Right, so in this video, I'm going to go through capacitors, topic 4. So, getting started, a capacitor is a device that stores, it holds on to the charge, and when you have the charge, you have an electric field that is stored, and that electric field means there will be energy involved in the field, just like from the previous topics. So a capacitor simply stores charge and energy. That's the whole point. The reason we have a capacitor is to store energy. In order to do that is we have to store the charge because they will repel with each other. They want to run away. So that is storing that energy. As soon as you connect the capacitor to something else, the electrons can pass through it in a circuit. So that's the whole point of a capacitor. Which is the following is the unit for capacitance. Coulomb is no, that's for charge. Farad is for capacitors, so this is good. Volt would just be for potential, and joule is energy. That's potential, energy. Not E, we don't call it E, we call it U. E is electric field here. So that means, in this case, B is the answer. Apparently that's a C. Anyway, over here, which is a symbol for a capacitor. Okay, so we have these 4 symbols. You should know them all. The first one is a resistor. Ew, that looks horrible. Let's do it the proper way. There we go. That much better. Yeah, the American way, the British way. This is good. This is not good. Do not draw this in an exam. I will be very angry with you. All right, so that is a resistor. So I'm just going to call it resistor. That's a T. This is my capacitor, so I'll just circle that. This is an inductor, which we're going to actually talk about in term 3. So right now, you don't really need to know much about what this is, inductor. It's similar to a resistor, and said that it resists the change of current. More on that later. This is just a battery. Not a battery, really. Actually, it's a cell. Battery or cell. A battery just means more than one. So if I had 2 of these next to each other, that would technically be the battery. But yeah, so it's the power source. B is the symbol. The figure shows a charge capacitor. What is the net charge? So you have plus here and minus here. You will have an equal amount. Maybe you'll have 100 over here, and that means I will attract minus 100 on this side. That's the idea of this. So you now have an electric field in here, which is where I'm going to have my energy from. Okay, so what's this? 100 and minus 100. Overall, the total net charge in this configuration should be 0. Now, looking at that, so 2Q is wrong. First of all, this is totally wrong anyway. Plus this minus the magnitude of this, that would actually give you 0. So that is wrong anyway. If this was 0, that could have been correct. Q is also wrong. These 2 are the only options we have. This is the values. This means magnitude only. So we're not talking about the magnitude only. If I was to do the magnitude only, this would be, actually, you know what, that's actually would have been right, because the magnitude and the magnitude of this, you would ignore the minus. This would be a correct formula, but unfortunately, it should equal to 0, not 2Q. So apologies for the little mistake earlier. So that is wrong anyway, because it should be 0. So that's not good. This is going to be wrong, because this should say 2Q. That should say 2Q, which is also wrong, because it should be 0, so that's definitely wrong. And that means A is the best answer. Plus 100, minus 100, 0. This is good. Okay, so let's move on. Simple circuits for this. Very nice. I love simple circuits. This is good. So we have a capacitor, we have a switch. A would lead me that way. B would lead me that way. What happens? So let's set it to A. So I'm going to set this. I'll follow a line here that way. I'm going to go towards A. This is my switch at A, and it takes me to the battery and back down again. So now that I'm going to the battery, it means I will be charging it. The battery will give energy to the capacitor. So the capacitor charges when it's at A is good. That means, obviously, it cannot be charging at B. But let's see what actually happens at B. Going this way now, this way, towards B, and this path, well, you can see that I am no longer connected to the battery, I'm connecting to itself, which means the electrons will redistribute across the wire. It will discharge. So that means this one's wrong. It will discharge at A. Well, that's obviously wrong because we've already said it charges at A. It discharges at B. That is correct because, like I just mentioned, they will redistribute amongst themselves. So which one's good? So we have this one and we have this one, 2 and 4. 2 and 4, which means the answer would be D in this case. Very nice. What is the voltage if you have the capacitance and the charge? Well, it's the formula Q equals CV. Q equals CV. I want V, so I'm going to solve for V. Oh, that's a V. All right. V equals Q over C. Q over C, we have 30 micro. I can keep the micro like this. It's times 10 to the minus 6, but you'll soon realize that these micros will just cancel anyway. The 0 will cancel anyway. 3 over 1 just gives you 3 volts. You don't even need the calculator for that. But yeah, go ahead and use the calculator just to make sure your answer is correct. But yeah, 3 volts. Over here, you have a parallel plate capacitor. You have this much charge. You have this voltage. What is the capacitance? Same formula, but now I want C. C equals Q over V. 240 nano. Nano is minus 9. That's nano, negative 9. N. Nano, negative 9. That's how I remember nano. N, 9. Nano divided by 12. And if you put that into your calculator, you should get 2 times 10 to the minus 8. Okay, very nice. Let's move on. Over here, a capacitor stores this charge at this V. What happens if the volt to the capacitor if the voltage is doubled? Interesting now. So, if the voltage is doubled, I clearly know that Q equals CV is directly proportional to the Q, so I will have more voltage, more charge. Makes sense. If I have a capacitor and I add charges onto it, and then they maybe get full up and they don't want to add any more, so I will need more energy to push more charge on. I can force more charges on with more energy. Say, no, you get on that plate and you have to stay there, like it or not. So that's what happens if you increase my energy. The voltage, I'll have more charge. These guys are very unhappy, but there's nothing they can do about it because I have increased the energy from the battery. So voltage is energy per coulomb. Each coulomb has energy. Very nice. So the charge would double. So that means charge doubling. Well, that A is wrong. The capacitance both fall to half. B is wrong. Capacitance and charge both double. Maybe C and maybe D. Now, what happens to the capacitance? Now, you might look at this and change this around to get C. Well, actually not true, because C is constant in this case. C actually doesn't depend on the energy. How do you create a capacitor? Consider a capacitor like this. Imagine like this is a wall, and we have another wall. And inside this, we're going to place charges. We're going to put some charges on here. No matter how many charges I add, no matter how much energy I use, I cannot physically change the size of this. This value depends on the distance between them, the area of the plates, which is the other formula, which we'll get to very soon. So the idea here is I cannot affect the capacitance by simply adding or removing charges. So think if you're in a classroom right now, you're sitting inside a classroom. I have students in the classroom. And if I want to make the classroom bigger, how can I make it bigger? Adding more students? Of course not. Having security stand outside the door to force you staying in the classroom? Of course not. I would have to break the wall down and make it a bigger room physically. That's how you can do it. So that's a long-winded way of me telling you that the capacitor stays the same and the charge will double. That's the answer. Okay, let's just swiftly move on, yeah? A parallel plate capacitor has this. What would be the capacitance if you double the area and the separation is quadrupled? Now, this is what's going to affect the value of the capacitance. And it's the formula that I said, which comes later, and that is now. C equals epsilon naught A over D. We did this in a little simulation. Epsilon is the permittivity of free space. It's a constant. It's a value. It's given to you. We can ignore it for now. What we'll do is we're going to see if I make the area bigger, if I make my area bigger, of course I will have more charge can be stored, or that's good. The capacitance is bigger. If I make the distance smaller, let's see what happens. So what we're going to do is I'm not going to make it smaller, actually. I'm going to make it bigger. So that's a problem now. If you make it bigger, the distance between the two plates is much further. That will reduce my capacitance. Set everything to 1 except the thing I want to change. Why? Because if I do 1 times 1 divided by 1, I will get 1. If I now make some changes, I will get the new relationship. So let's do that over here. What I'm going to do now, I'll get that out of the way. I'll keep this as 1. I know it's like 8.85 times 10 to the minus 12. I don't care. I'm going to call it 1. times the area. What did I do to the area? What did I do to the area? I doubled the area there. So the area was doubled, times 2, divided by quadruple over 4. 2 over 4 just becomes a half. So you can put that in your calculator and you will get a half, or you can just realize that it becomes a half. So that means a half of C, which is the same idea as C over 2. C divided by 2, a half C. Same. B is the answer. The capacitor can be increased by, so how can I increase the capacitance? So as you can see, by just plugging some numbers in, you can figure out what happens. If I was to use the same formula, increasing my area will increase the capacitance, making that top number bigger. Decreasing this will make this. Why? Because I am dividing by d. These are inversely proportional. Decreasing my distance will increase the capacitance. As you just seen, increasing the distance decreased my capacitance. So keep that in mind. Now it says we want to increase the capacitance. Increasing the charge does not affect it. Decreasing the charge does not affect it. Increasing the separation, which is making the distance bigger, well, actually, no, we realize that that's wrong. Decreasing the separation, yes. And you know what? Let's just check. C equals EA. 1 times 1 divided by, let's double the plate separation. Let's double the plate separation. That means, actually no, that's not what I want to do. Oh, if I double the plate separation, that just becomes a half C, right? That's making it smaller. Now let's do it again. Let's do 1 times 1, and let's half the plate separation. Let's decrease the plate separation to a half. And if I was to put that in my calculator, I will get, well, 2C. Look at that. I decreased my separation and I increased my capacitance. So that's a way to check with maths. So let's just get rid of this because it will end up annoying me later. I always do that to myself. There we go. So, moving on. Which of the following are proportional to the capacitance of a parallel plate capacitor? The proportional, directly proportional, I kind of gave it away up here. The area is directly proportional. The separation is inversely proportional, and these two do not affect it. Okay, if you charge it, and then you remove the battery, you then move the plates far apart. You can do it using formulas, or you can just think about it like this. If I have here and here, this is plus V and this is minus V. I have there. But what I have done, this is the first plate and this is the second plate. But what I'm going to do is I'm going to increase them. I'm going to put them further away. So you can see that either move them further apart. I am now going to place my plus V over here, and I'm going to place my minus V on the other side. Look what I've done. Minus V. I have made such a big distance here. I have made a big distance. So the voltage difference, the potential difference, clearly will increase, because this might be like a small potential difference from here to here, but I have a big potential difference from here to here because of the formula V equals ED, VED, V equals ED. So I have basically increased my distance, I have increased the V. So that's how you can figure it out, even just using the formula, using VED. That means the answer is A. Moving over to here, suppose you have a parallel plate capacitor, but you want to reduce the area of the capacitance. How can I retain the same value? So I can just use the formula here. C equals E, that's the epsilon, EA over, I'll make that epsilon, EA over D. Same rule. So what have I done? I have to reduce this. So if I reduce this, that becomes 1 times a half divided by, well, it's supposed to be 1, that becomes a half. What can I do to my D to make it 1 again? If I doubled it, that's bad, because it will reduce further. It will become a quarter. If I half this, what happens? A half divided by a half, that cancels. That becomes 1 again. So that means I can reduce the D by a half. These two will just cancel, and you will just get 1. So A is the best answer. Moving on to the final question here on this page. A parallel plate capacitor is connected here. Which of the following is true while the battery is still connected? So the V is constant, it will not change. So if that's the case, we know that the potential difference will not be half because the battery is supplying it. The capacitance obviously will not change as a result, as we know. It will, even if it does, it will be less if you were to forget, I'm not going to get into that. The potential difference across the plates does not change. The potential difference will actually, it could change. That's interesting. Potential difference across the plates does not change. Which of the following is true? So potential difference. Well, it could change. It'll be different values. Yeah, maybe. That's actually an interesting question. I'm going to actually double check that one. I'm going to double check that one because the electric field, if that was to change, the potential difference will change. E equals V over D. So this question is not a very good question. You could have said A or you could have said D. I'm going to close this one off because there's some sort of issue with this. Or maybe I just don't understand it. If you can figure it out, tell me. I need to run out of time, so I need to turn this off and start again in the next video.